Okay, sorry for the disturbance. Somehow my machine entirely just crashed completely. Okay, so coming back to this thing question, which has how do you give masses to the fermions, and then we ask the question how to give masses to the. We know that this is still unanswered, but if we give masses explicitly, this because this breaks symmetry, as we have said, this breaks symmetry. Uh, Symmetry. Similarly, if he gives masses explicitly, which is a symmetry breaking masses explicitly, okay, what happens is that the theory is not renunciable. And as I said, I think we had a discussion on renunciability earlier. Uh, if a theory is not renunciable, that means that you cannot observe all the infinities which come from higher order corrections. So in field theory, remember that there could be higher order corrections. Next level in perturbation theory, like for example in QED we have seen corrections coming from process diagrams like this, and then when this enter process, like say E plus E minus going to mu plus mu minus, okay, they introduce a lot of infinities, and these infinities need to be absorbed into physical parameters of the theory. Okay, the same thing happens when any gauge theory, in any quantum field theory. Like for example, if you have this neutron decay, say for example neutron going into a decay, even in Fermi theory, say, so you can have corrections of this type. So there are all these corrections which need to be absorbed, and so on. So okay, so these corrections have to be absorbed. You have to all this one loop corrections give rise to infinities, and these infinities have to be absorbed in terms to give you the physical parameters of the theory, or in terms of can have to be absorbed in terms of the parameters of the theory. Now, the number of parameters of the theory are like the wave functions, the coupling constants, and the masses should always be larger or equal to the number of infinities one generates. Only then the theory is renunciable. But if you have, if you add masses explicitly, such a theory is not really renunciable, because you are adding masses. Okay, it's when you add, okay, because the main cause is that when you add masses explicitly, you are breaking symmetry explicitly. There is no still underlying symmetry which protects these masses. So in a way, I cannot say anything. I mean, I'm trying to explain it in a much simpler fashion. There is no underlying symmetry factor which really protects these masses. So what we need is that the masses to be generated, but there should be still an underlying symmetry factor which protects these masses. Similarly, like for the gauge boson, for the even for also for the fermion masses. Okay, so we need a renormalizable way of generating masses. A renormalizable method of generating masses for gauge bosons and fermions. Now here again our experience with strong interactions plays a role. Remember the theory we have seen is the 5-4 theory, okay, where there's something we encountered called spontaneous symmetry breaking. What does spontaneous symmetry breaking do? Spontaneous symmetry breaking tells you only the ground state breaks the symmetry, but all the higher states really have the symmetry is intact. So you can somehow, if you can organize in such a way that the ground state of the theory, these masses are generated, the fermion masses and the gauge boson masses are generated, but all the higher states are sort of symmetry conserving. Then you have a way of protecting these masses at the same time, because in the limit of exact symmetry, these masses are sort of sent to zero, and when the symmetry is broken spontaneously, these masses get generated. So this is the basic idea. But then you had the issue with but then things are not so easy, because spontaneous symmetry breaking, if you remember, normally leaves, because the example we have chosen was a global symmetry. Okay, remember we didn't see it in a gauge theory. We have seen it in a global symmetry, that whenever there is spontaneous symmetry breaking, it leads to something massless particles, which we saw it as Goldstone bosons. Okay, we have seen this thing as a Goldstone bosons. And then there was also this Goldstone theorem. This is true for any local or global symmetry, but if it is a local symmetry, if it is a gauge theory, okay, there was something which was shown by Higgs mechanism. He showed that these massless particles disappear from the theory, and the massive massless particles in the theory become massive. Like for example, if you take a 5-4 theory with scalar QED, the same example which we have seen all through, but now incorporate spontaneous symmetry breaking in that, the photon which is massless becomes massive, and the Goldstone boson which gets generated completely disappears from the theory. So that is the basic idea of the Higgs mechanism. Okay. So let's just revise the Higgs mechanism using scalar QED. Scalar QED, if you remember, is del mu phi whole dagger del mu phi minus m square phi dagger phi. But now we want to incorporate spontaneous symmetry breaking. So let me also add one more term, lambda phi dagger phi whole square, because I want to incorporate spontaneous symmetry breaking. So I also have this term, and this term is also gauge invariant, meaning that is invariant under U1 interactions. So del mu, because it's just a U1, means del mu plus Ig Q A mu, and e power I theta of x Q. So meaning that's it. So this is the generator because we just have one single generator, meaning where Q is the charge of the field essentially. So this is just where theta of x is the local gauge transformation. This is the gauge transformation. So up to here is your normal scalar QED. Okay, up to here is your normal scalar QED, but now because we want to incorporate spontaneous symmetry breaking, we added this lambda phi dagger phi whole square term, or the one which is underlined by, say, blue lines. Now let's do the spontaneous symmetry breaking. So the spontaneous symmetry breaking, we just focus on again this has been done in one of the lectures. So V of y is equal to minus m square phi dagger phi plus lambda phi dagger phi whole square. Phi is expressed in terms of, say, real and imaginary parts, no? So we have phi r plus I phi I, and then phi r I re-express it in terms of V times H. H is some field, and in the vacuum or at the lowest energy state, vacuum is nothing but the lowest energy. Phi I in the vacuum is essentially 0. Plus, if you had some term xi, this xi is the Goldstone field. As we have seen, this xi becomes massless actually. But anyway, as of now, let's not worry about this thing. What happens is this xi just gets removed in this theory. Okay, gets removed by the Higgs mechanism. So we can further about it. So it gets removed, and now what we have is this A field. Let's just see what happens to this A field. Okay, let's just see what happens to this A field. The A field what happens to the photon? What happens to the photon? Let's just see what happens to the photon. So we should remember that V is equal to square root of minus m square by lambda. Maybe there's a factor to lambda. Okay, I'm going through it a little bit fast because almost all the concepts which we have dealt in the previous lecture and this lecture had been covered in other lectures. So it is just an amalgamation of all the previous concepts. So we are just putting together all these concepts. So let's see what happens to the photon. So for that, I need to see the kinetic term. So that is del mu phi whole dagger del mu phi. Let me just expand this a little bit. Del mu phi plus I g a mu phi whole dagger del mu phi plus I g a mu phi. So this is equal to, now you have your standard del mu phi dagger del mu phi plus you have a term which is g square a mu dagger a mu phi dagger phi, plus then there is the derivative term which is essentially Ig. Okay, this is a real this g square is a real term. So Ig del mu phi dagger a mu phi plus hc. Okay, so there is this term which is the third term essentially. Now let's look at this second term which you have written. So this term, let's look at this term. Okay, this term is g square phi dagger phi a mu. Now phi is equal to v plus h, the real part, plus I. Xi is 0 essentially in the vacuum. So in the vacuum it's 0. So this gives me, say, constant. So field expansion around vacuum. So essentially you are just taking tiny perturbations and calling them as field, the field essentially around the vacuum. So this gives me the terms g square v square, which is a constant. Okay, normally it is there is a half factor or something sitting here. So a mu plus g square h square is a field for, okay, a mu. So this g square v square so this g square v square, because it's a constant, is like a mass term. If I call it as ma square, maybe there is a half here. Okay, it's called half g square v square. Maybe if I call it as v by root 2 and everything. Okay, so g square v square is the mass of the photon. So what is it we are saying? We are saying that okay, let's so what we are saying is that a massless gauge boson attains mass in the vacuum. Okay, that's one of the first steps we are saying. Okay, and the second step what we are seeing is that a particle which has 2 degrees of freedom, phi, which has phi r plus I phi I, just becomes a real scalar field. So the imaginary component just disappears. Okay, so it would be nicer even if we do the counting of the degrees of freedom. Actually, it would be nice fun. So you have phi, a real scalar field, a complex scalar field which has 2 degrees of freedom, a mu, which is a massless spin 1 particle which has 2 degrees of freedom. This is before symmetry breaking. And then after symmetry breaking, phi has become 1 degree of freedom because it has become a real scalar field instead of a complex scalar field, and a mu, which was initially a massless vector particle, okay, spin 1 particle, has become massive spin 1 particle, so it has 3 degrees of freedom. So the degrees of freedom in the have remained constant. They are conserved. The total number of degrees of freedom before and after the symmetry breaking is the same. Okay, but they got just reorganized. They had just got reorganized in such a way that the photon became massive, and there is one real scalar field. This is the essence of Higgs mechanism, and such a theory with spontaneous symmetry breaking is in fact renormalizable. Such a theory is actually in fact renormalizable. So this is the, of course, this was shown much later by Truth and Weidman, but the Higgs mechanism itself was a good starting point to build the standard model by Salam and Weinberg. Weinberg-Salam model came up. Okay. So what you have essentially is that in the Weinberg-Salam model, uh, so so the Weinberg-Salam model, which is the precursor, or essentially is the standard model, say model of one generation. So the main features of this thing is that it predicted the masses of the gauge bosons Mz and Mw. So it also sin square theta w, the mixing angle between weak and electromagnetic coupling constants. So it predicted these two, and in fact, they actually found this W and Z bosons immediately after that. So they had this model in 1960s, 67, 68. Okay, Weinberg in 67, 66, Salam, I think, in 68 or something. The renunciability, in fact, was shown in 71, sometime later. Okay. By mid 70s, they already found neutral currents, and by 83, they discovered these particles actually. And so these particles were discovered in 83. So let's look at this theory a little bit more detail. So again, we start with the leptons. The leptons would have so nu e, then okay, one generation. Let's just take one generation. Then er. See, this is left-handed and this is right-handed. Now, in addition to that, we also have a Higgs. So Higgs is an SU2 doublet complex scalar. So this is the main thing which Weinberg introduced, okay, inspired by the Higgs mechanism. Okay, so he introduced a complex scalar, so which has two complex scalars up and down. Okay, this is a complex scalars. Both of them are complex scalars, and he assigned the metric charges phi plus and phi 0. Okay, he could afford to do that because they have this is still a complex scalar because it has a non-zero hypercharge. Okay, it has a non-zero hypercharge of electric charges could be plus and 0. It looks like a neutral complex scalar, but it's not actually a neutral complex scalar. It is a neutral complex scalar only for electromagnetic theory, but for hypercharge theory, it is still charged because it has a charge plus half. So with this, one writes down the most general Lagrangian, which is gauge invariant. So this Lagrangian turns out to be SM1 generation L bar I del slash L, okay, plus ER bar I del slash tilde ER plus H dag scalars del mu, the same del H whole dagger del mu H. Now we also want spontaneous symmetry breaking. So that is the reason why we give minus V of H, where V of H is M square H square H plus lambda H dagger H whole square. So this essentially is the standard model, but then there is also one more term which is possible, which is plus L Yukawa. Remember, we introduced Yukawa interactions when we were discussing pion neutron scatterings. So this is very similar, and so you have L Yukawa, which is also gauge invariant, will be L dot H by E R. Okay, so this is the full standard model Lagrangian, this part, okay, for one generation. How come this is let me just make just a circle. Okay, now this is the Lagrangian when the symmetry is unbroken. That means we have not yet incorporated spontaneous symmetry breaking. Now the symmetry of the standard model, again, just to repeat ourselves, is S2 L times U1Y so look at so what we have. Okay, so now what happens in the symmetry breaking phase? Like I said, okay, let me just finish this writing. This del mu is equal to I tau a w mu a plus I g prime y mu and del mu tilde is only Ig prime y b mu. So this is the C2 cross E1. Now let's look at the symmetry breaking part. The symmetry breaking part comes from the Higgs part. The Higgs has H dagger, H doublet. This is say H1 plus H real plus IH imaginary, and then there is this entire thing is charged, and then there is this, let me call it H plus, then there is H0 real plus IH0 imaginary 0. So in the vacuum, because we don't want to break electromagnetic theory and everything, so in the vacuum we will give the vacuum, only this gets a non-zero vacuum expectation value. Okay, only this part gets a vacuum expectation value, the real part of the Higgs mechanism, the neutral Higgs boson, neutral Higgs boson real part. All these three eventually will end up being so Goldstone bosons. Okay, these will become Goldstone bosons. So the masslessness of W, which is massless at this particular point, Okay, because all it's completely massless because we have not added any mass term, will become massive in the limit when uh, the HR 0 gets a vacuum expectation value, and these three modes will be eaten up by W mu. Okay. So in the vacuum, H would be 0 plus 0, V plus H plus 0, I. So this is in a particular gauge called unitary gauge, but it doesn't matter. So all the Goldstone modes have Higgs mechanism. So essentially all the Goldstone modes get eaten away, disappear, and become, and at the same time what happens is W bosons become massive. Now in fact we can actually put it back into this theory in a careful way. Okay, so let's look at the kinetic term of the Higgs. So how do they get del mu H dagger? Just like the scalar QED case we have seen so far, except that in this case it's a there are two gauge bosons, meaning there are two what do you call gauge groups, and one of them is an non-abelian group, which is SU2. Plus Ig prime y b mu a, so this entire thing times acting on H, so this entire thing acting on H, so H dagger, again the same thing acting on H. So if you remove the basic parts and everything, remember that this is just a matrix, this is a matrix, this is also a matrix. So H dagger would come on this side. So when you expand this thing, okay, so you will end up having terms of this type, essentially, that there will be slightly complicated. It's a detailed algebra. I'm trying to skip as much as possible. You have a non-diagonal element here. You have G square V square W mu 3 0 square, which we said that it will be somewhat like the neutral component, and this is the charged component W plus and W minus. So if you want to make physical, so this will be like the mass term for the W bosons, and this will be the mass term, meaning this another term which would be coming from B mu. Now when you diagonalize this, so this diagonalization will depend upon G prime and G. So you have to diagonalize it by some matrix which will be some cos theta W, sin theta W, sin theta W, cos theta W, some sort of a matrix of this type. So diagonalizing matrix. Where this is the same angle which we introduced earlier, this is tan theta W is equal to G prime by G. So same angle. So when you diagonalize this, you'll end up having mw square, or let me write down explicitly. So you'll have something like 1 by 2 g square v square w mu, which is positive and negative. So this is the mass for the this is the mass for the W bosons. Then there will be a term 1 by 2 g square plus g prime square v square. So z mu nu, z mu nu. What is z mu nu? Z mu nu is the linear decomposition of the neutral components, and then there will be the massless photon. Photon remains massless, where z mu nu is the linear composition. Z mu nu is equal to some cos theta w. W mu 3 plus sin theta w. Oh, sorry, B mu. 1 by root 2. And then A mu would be the opposite combination, sin theta w. Cos theta w. Okay, after the diagonalization, because these matrices are not diagonal, no, what we have seen earlier in this kind of thing, when you write down all the fields and expand them and everything, these matrices are not diagonal, and when you actually diagonalize them with using this matrix of cos theta w, sin theta w, this is what happens. And we can actually okay, so this E is the neutral gauge boson, the mu neutral gauge boson Z mu. And A mu is the mediator of EM theory. So you have recovered your EM theory. Now if you want to fully recover, you can actually fully make the comparison between electromagnetic theory and meaning ultra-weak theory and weak interactions. You can connect with the interactions. Okay, you can compare interactions and then make a this thing. Like for example, from what we have seen, we'll have g square by mw square would be equivalent to gf, and then we also have g prime sin theta w is equal to the electromagnetic coupling constant. So with this, now you can actually fix what is this Weeks mixing angle, because we know GF, we know this data. Okay, we know electric this is nothing but alpha, which is 1 by 137 at the weak scale. GF is of the order of 10 power minus 5 mp squared. Okay, mp power minus 2. So this is g 10 power minus 5 g power minus 2. So we know what these values are. So with this we can actually see what is this sin square theta w. Sin square theta w comes out to be 0.22, Okay, and from this you can actually calculate MW mass to be 80 GeV square. MW square is equal to 80 GeV square, and mz square comes out to be 90 GeV square. Okay, and you also have what is V. Okay, so V comes out to be V by root 2 is around 175 GeV. Okay, all these are fixed just from the data essentially coming from GF and E, and sin square theta W comes out to be 0.22, and this is the prediction, Weinberg's prediction actually, just by equating it to the Fermi theory and the electromagnetic theory. It's into two different contributions. So V comes out to be 1 by 175 GeV. So at that particular point when Weinberg and Salam produced this theory, they didn't still know whether the theory is renormable or not. In the 1970s, okay, 71, 72, Tooth and Weltman passed away recently actually, proved that spontaneously broken non-abelian gauge theories are renormable. So that showed that Weinberg's theory or Weinberg-Salam theory is a renormalizable theory. See, with QCD we didn't have this problem because QCD is already a renormalizable theory, and neither we had a problem with the QED, which was shown to be renormalizable by Feynman, Schwinger, and all these guys. So, but standard model, it took much larger and much technically much more harder to prove that it is a renormalizable theory, and it has been shown that since it has been shown as it's a renormalizable theory, it started being accepted as a physical theory. So it not just as a model, but it's some sort of a theory which could be tested. So the first test was neutral currents, then discovery of W and Z bosons, essentially at the energy, the mass ranges which was predicted by Weinberg. Then it was tested at the loop level, in the sense with higher and higher precision. Okay, so with very strong precision, people started testing the Strand model, and recently all these tests have been successful, and recently they had proven the discovery of the Higgs boson. So with this sort of the entire standard model stood on a very strong footing. There are other phenomenological features of the standard model which and also there are a lot of other things which could be covered, like for example neutron masses, which is not yet discovered, and then the CP violation, which has still some important points which are not yet done. Okay, so these things I'll cover a part of it. I won't do a full lecture on them because These are, each of them requires a huge class on this, and also it's quite involved actually. I wouldn't, for the first course in meaning on the standard model, I wouldn't, because there is going to be another course on standard model for people specializing in particle physics. So this is just a precursor for it. So I would let's just leave it as it is. Okay. So let me stop here, and there are a lot of things which are still unsolved with standard model, like neutrino masses, CP. Meaning CP evaluation has been done, but there are other things unsolved. I'll just list them. Problems like, for example, large number of parameters, to baryon symmetry, and then there is the issue of CP evaluation in some sectors which are not completely understood. Then there is, of course, dark matter. Then how to include neutrino masses. So these are all issues which are still, each of them would be a very topic on its own. Okay, these are issues which are not completely understood, and there are people, there are a lot of models, but there are not enough experiments to attack these problems actually. So all the studies to solve these problems, something like BSM models, BSM physics. So beyond standard model. So this is something called beyond standard model physics. So in this, people try to find extensions of the standard model which try to solve one of these issues. Okay. I didn't cover CK, meaning flavor mixing, K physics, CP violation, uh, all these things which are quite involved. Okay, but at this level, I think I'm happy with whatever I covered. I don't think I would be more willing to cover more than this. Okay, and maybe a more detailed course on standard model, which would happen in the next semester, would cover all these topics in much more greater detail. Actually, okay, I'll stop here, and thanks for listening to this course.